Hi, today I want to talk about chair conformations. So there are two ways you could draw a chair conformation. The first is to draw two parallel lines like this, and make a short one, and then create a longer one. And this can interchange with a similar structure, except for you draw the parallel lines this way, with the short ones this way, and then the long ones on the right. So these are the two conformations that a chair can have, and this is called a chair flip when you switch between the two. And there are two different positions that you should consider. One is the axial, which is straight up or down in this case, or equatorial, which is slightly slanted downwards. And for the one on the bottom, this is slightly slanted upwards. And this is true if you're going around the molecule. I like to select the rightmost carbon, in this case 1, 2, 3, 4, 5, 6. So the rightmost carbon as carbon number 1. So in the case on the right, 1, 2, 3, 4, 5, 6. And starting from 1, I like to go up, which is already up in this case, and then down, up, down, up, and down. And let me change to a different color. And to choose the equatorial, since it's up already, you go down, up, down, up, down, up. And this is the same case for the chair on the right, except for since it's the starting point is down, you want to go down first too. It's down, up, down, up, down, up. And that's for the axial position. Now if you switch over to the equatorial position, since this line is already down, the only conformation is up. And then it goes down, up, and down. And so that's how you draw the basics of a chair conformation. Now how do you determine whether the molecule is more stable in the axial or equatorial position? Take a CH3 like this. Would this be more stable, or would it be more stable to have it be downwards in the equatorial position? And a basic rule to know that it is usually always more stable if the substituent is in the equatorial position, and that is due to steric hindrance, since the other molecules up here can interact with each other, and this is known as the 1,3 angle strain, 1,3 diaxial strain. And so when it's in the steric position, it usually does not have the strain, since this one is going down and this one is going up. So this molecule is the more stable one because it is in the equatorial position. Now what happens if we add a second group? Say we add a bulky group in the equatorial position, like say a terp-butyl group. And then so the terp-butyl group would be down in the axial position in this case. So this one is in the axial and this one is in the equatorial, while this one is in the axial and this one is in the equatorial. So which one will be favored? In this case, since the bulky group is in the equatorial position, that is more stable, so you can look to decide based on the bulkiness. Since you don't want the axial position, say this one, to have the 1,3 diaxial strain with these right here. There will be an interaction between the two right there. So in this case, with a bulkier group, this would be the more stable chair conformation.